Morning, students. My name is Chris Allen, and I'm going to be your Calculus BC teacher. Today we are going to start Calculus, and just to let you know, we are actually going to start in Chapter 3. We are, due to our new schedule, under some time constraints, I'm skipping Chapter 1, which is on limits. We will talk about some limits later on in the course when we get to indeterminate forms, but that's really not the focus of the BC curriculum. We will skip Chapter 2, which is basic derivative rules. Things like, what's the derivative of e to the x? You guys should know that already. But I will integrate, pun intended, I will integrate that review within our Chapter 3. We're starting with Chapter 3. In fact, today we're going to start with Section 3.3 and 3.4. So I'm going to go ahead and share my screen here with you, hopefully. Okay, so these notes are available, so feel free to grab these if you'd like a copy. So today we're going to look at the first, I just narrowed it down to those two things, first and second derivative test, but honestly there's actually a lot going on in these two sections. Again, this is all review. We want to be able to figure out where functions are increasing and decreasing. We want to be able to use the first derivative test. We want to be able to figure out where functions are concave up or concave down. We want to be able to find points of inflection. We also want to be able to apply the second derivative test to find extrema. So again, a lot of stuff, but I think it'll come back to you pretty quickly. So let's go ahead and start with increasing and decreasing. So theorem 3.5. So if we look over here at the function f where it's increasing, if I was to draw a tangent line, pretend that line's tangent line anywhere on this part of the graph over here will be the slope of that tangent. Well, it's going to be positive, so that gives us bullet point number 1. So if we have a function that has an f prime that's greater than 0, like over here in this situation, then we call the function increasing on that interval. If f prime is less than 0, like over here, we call it decreasing. And if f prime is equal to 0, that would be case 3 down here, we call it a constant. So let's look at an example of that. By the way, that should look familiar because that's basically the exact same notes we used last year. So let's say I want to figure out where my function f of x is increasing or decreasing from 0 to 2 pi. Well, the first thing you want to do is you want to find your critical numbers. So critical numbers in this case is when f prime is equal to 0 or is d and e. Well, f prime, the derivative of sine is, hopefully you're thinking cosine of x. So I want to ask myself, when is that equal to 0 or d and e? Well, it's never d and e, so I can get rid of that. When is cosine equal to 0? Well, when x is equal to pi over 2 or 3 pi over 2. So now that I know those two critical numbers, I'm going to do my little sine chart here. So here's 0, here's 2 pi, let's say, because we're restricted to that domain. And all I'm going to do now is I'm just going to plug something like this is pi over 2, here's 3 pi over 2. So what's a number that's less than pi over 2? Well, pi over 4. So if I do f prime of pi over 4, that's the cosine of pi over 4. Well, what is the cosine of pi over 4? Well, it turns out that it's a positive number. Hopefully you know what that is. I think it's a radical or something, but it's positive. So this is positive. And if that's positive, then based on our last theorem, we know that the function's increasing there. We play the same game here, and we find, in fact, let me go ahead and do that one there. A good number to plug in there would be, let's say, pi. So what is the cosine of pi? Well, the cosine of pi turns out to be a negative number. So that implies that this is decreasing. This also turns out to be increasing. So therefore, we can go ahead and answer our question now. Therefore, we can conclude, I'm trying to do 3 dots, but my computer's not letting me do that. I'm going to say that f of x is increasing from 0 to pi over 2 and 3 pi over 2 to 2 pi. And then it's decreasing here in the middle. I'm just going to write that here. It's decreasing from pi over 2 to 3 pi over 2. Sorry about the handwriting there. I'm running out of room. So that should seem familiar to you. So here are the guidelines. I'm not going to read through these. It's basically what we just did. Okay, first derivative test. First derivative test we use to calculate extrema. And the first derivative test basically says that if we see a change in sign from negative to positive, a change in sign of the first derivative, then it's a relative min. And if there's a f prime changes from positive to negative, then it's a relative max, which should kind of make sense. If you're going from an increasing function to a decreasing function, you had a maximum there in the middle. So here was a picture. This was in the notes from last year, so I'm sure you're familiar with that. So let's consider our new function here. I called it g. And we want to find the extrema of this. So I think I may have included, I did not. Oops, I hit backwards. Yeah, I included a graph. So this is the graph of g of x. Okay, so you can see that it's decreasing, then it goes to increasing, and then decreasing, and then to increasing again. Now the reason I'm wanting to point this out is let's say you're going to use your calculator because this function is a little bit harder to deal with, right? So what you want to do is you want to find your critical number. So let's go ahead and see if we can do that with our calculator. We do the critical numbers here by, I plugged in the g function in y1 and then I did its derivative. Now look what happens when I graph this. Now it's kind of hard to see, but I try to make the derivative graph this thicker, bolder lines. And you can see that there's something going on there, and there's something going on there, and maybe something going on there. Remember, critical numbers is where g prime is equal to 0 or d and e. Now, the reason I'm pointing this one out to you on this one is, guess what g prime is right here when x is equal to -2? Well, it's not 0, it's actually d and e. I'm hoping that you notice that that looks like a vertical asymptote. And just to convince you of that, if you were to calculate the derivative of this function manually, which by the way, you would have to do the chain rule, you get the following. You get 4x over 3 times the quantity x squared minus 4 to the 1/3 power. So you can see that we have that critical number there of x equals 0. So that's when the derivative was 0. But then these two guys here, that's when x is equal to -2 and 2. Those are your other set of critical numbers. And basically, I'm not going to finish this example. I just wanted to point that out. But you do your sign chart again. In fact, let me just do one part of this. We had critical numbers at -2, 0, and 2. Let's look at 2. And again, I'm going to go back to when there was just the original graph. I mean, everyone I think can clearly see, I hope, that that's going to be a minimum, right? Well, it turns out that the first derivative here is, this is g prime, right, is negative. That tells us that g is decreasing. And then over here it was positive, g prime was positive, so it's increasing. So guess what this turns out to be? So x equals 2 is a relative min. Okay, moving on. By the way, there's 3 answers there. This is an example of a problem from the AP exam. It's multiple choice. The only thing I kind of want to point out here is that these are all derivative graphs, and I will let you, if you want to pause the video and try to figure out what the answer is from that. We need to move on, though, to concavity. So here's the definition of concavity. Something is concave up when f prime is increasing on an interval, and if it's negative, then it's decreasing. So test for concavity. Basically, and this is what you should already know, but if f double prime is greater than 0, it's concave up. If f double prime is less than 0, it's concave down. There is a third case, and that would be if f double prime is equal to 0. It just basically means that it does not have concavity there, like a line would not be concave up or concave down. So example 3 here says determine the concavity. So we've got f of x equals, and I've got this exponential function. Now I put this exponential function here because I want to illustrate that you would need to do the chain rule. And I'm only going to do the chain rule once here, and I'm going to cheat on the second part to speed this up. But f prime of x, well, the derivative of e to anything is just itself. And then you have to do the chain rule. So then you have to do the derivative of the top thing. Well, the derivative of the top thing turns out to be negative x. In other words, this derivative is negative x e to the negative x squared over 2. So that's your first derivative. Let's go ahead and do the second derivative. The second derivative, I'm going to cheat. It turns out to be e to the negative x squared over 2 again, but this time it's going to be multiplied by x squared minus 1. So now here's where we're going to actually use this information. First of all, this here, this e to the negative x squared over 2, that is never equal to 0. Okay, e to the x functions are never equal to 0 unless they've been shifted by, but that's not the case here. So when is this going to be equal to 0? Or d&e for that case? Well, that's going to be x equals plus or minus 1. So we're going to put our table here again. We're going to do negative 1 and we're going to do 1. And we're going to do the same thing we've done before. So like, what's a number that's between negative 1 and 1? So that'd be 0. So if I plug 0 into this, first of all, this is going to be something positive. If I plug 0 into this, that's going to be something negative in the middle. So I've got a positive something times a negative something. So that's got to be negative here. I'm going to use a different color here. Let's change screen. So this is negative. So that tells us it's concave down. And then if we picked a big number like 1,000, it turns out that this is going to be positive, so it's going to be concave up. It turns out it's going to be positive here, so it's concave up. So we know that f is concave up from negative infinity to negative 1, union 1 to infinity. We know that it's concave down. I'm running out of room here. It's going to be concave down between negative 1 and 1. Okay. I guess I could have used the next slide, but we're going to go on. By the way, here's the graph of that curve. All right, points of inflection. This is, by definition, it's just where the concavity changes, so that's no big surprise. So if it goes from concave up to concave down, we call this a point of inflection or a POI. Points of inflection. So this theorem basically saying that if we have a function that has a value x and some value y, and it's a point of inflection, then either the second derivative is equal to 0 or the second derivative does not exist. So, I mean, that kind of makes sense if you think about it. It's either going to have a horizontal tangent line there, or I'm sorry, it's either going to have no concavity there or it's not going to exist there because we're talking about the second derivative. Okay, so example 4 says determine the points of inflection of concave and discuss concavity for the graph of x to the third times the quantity x minus 4. Now, if I wanted to, I could go ahead and distribute this, but I want to remind you of something called the product rule. And if you guys remember the product rule, that's 1d2 plus 2d1. So to find h prime, I'm going to do 1, which is 3x, I'm sorry, x to the third, times the derivative of the second, which is just 1, plus 2, which is x minus 4, times the derivative of 1, which is going to be 3x squared. Then if we clean that up, that's going to give us the following. It's going to give us 4x to the third minus 12x squared. Let's go ahead and find the second derivative now, just using our power rule. And we're getting on 15 minutes here, guys, so I apologize that this is going long. But wait, basically what I've done is I've tried to combine 2 lessons into one. 12x squared minus 24x, which could be rewritten as 12x times minus 2. So we can see that we have some critical numbers of the second derivative at x equals 0 and at x equals 2. And so once again, what we're going to do is we're going to do our little chart. We're going to put 0 here. We're going to put 2 there. And then we're going to start making values in between and testing it with this second derivative. It turns out that this one's positive, so that means it's concave up. This one's negative, it's concave down. This one's positive, it's concave up. This function is continuous, so it's going to have a POI at both places because we can clearly see that the concavity has changed. So we're going to have POIs at x equals 0 and x equals 2. And we can see that it's concave up from negative infinity to 0 and from 2 to infinity. And then in between it's concave down. So let's go ahead and go to the very last thing that we need to do. And this is the graph here. So it's concave up here. It's concave down here. And it's concave up there. And we've got POIs here and here. Okay. Last thing, second derivative test. So if you've hung on this long, I appreciate it. So this video is a little long, I know, but we're going to finish it out. So the second derivative test is a little bit different than the first derivative. The second derivative test, what you do is you find your critical numbers using the first derivative, okay? Then you plug those critical numbers into the second derivative. If when you plug those critical numbers into the second derivative, it's greater than 0, it's going to be a relative min because it's going to be concave up, so you know that's going to be the bottom point. If you plug the critical number into the second derivative and it's less than 0, well, that tells you that it's concave down, so that's going to be a relative max. Unfortunately, though, if you plug it into the second derivative and you get 0, then it's neither, and you have to go back and use the first derivative test. So let's go ahead and look at this very last example here. I'm going to expedite this as much as possible. Let's just go ahead and do this here. Let's go ahead and find our critical numbers. So f prime here is going to be negative 15x to the fourth plus 15x squared. So that could be rewritten as 15x squared times the quantity 1 minus x squared. Okay, so there's our first derivative. That tells us that we have critical numbers at x equals 0 and plus or minus 1. We know we have critical numbers at 0 and plus or minus 1. So remember, we're doing the second derivative test. So to do the second derivative test, I've got to figure out my second derivative. So let's go and figure out what that is. And I'm going to use this right here. So the second derivative there is going to be negative 60x to the third plus 30x. Be rewritten as 30x times the quantity 1 minus 2x squared. And now what we're going to do is we're going to start plugging these critical numbers into this second derivative. So let's just do the point 0. So f double prime of 0. I'm plugging that first critical number into f double prime. Well, if you plug 0 in there, guess what you get? You get 0. And since you get 0, the second derivative test fails, and you would have to go back and use the first derivative test. I'm going to skip that for now because we're getting close to 20 minutes. However, if I plug in f double prime of, let's say, 1, let's do 1. If I plug that in there, I'm going to get 30. That'd be 30 times, and then 1 minus 2. So I think that that's going to give us a negative value, so that's less than 0. So that means that this is going to be concave down, which tells us that at x equals 1, we have a relative max using the second derivative test. Now I'm going to show you the graph of this. It's right here. So you can see that we did indeed get that relative max. It turns out that x equals negative 1 is the relative min. But notice that at 0, the second derivative test failed. So we have to do that again. All right, guys, that was a lot of information. I'm going to just stop that video. It's your job now to review all of those things. First and second derivative test, increasing, decreasing, concavity, and POS. Have a good day.